The first problem is formulate and solve a linear programming model for Begsaber's production problem on a spreadsheet. First, we have the total required nylon equals units produced multiplied by nylon used for each product. The same can be said for total labor hours. Finally, we have total profit equals units produced multiplied by unit profit. Now, we will calculate the max profit using Solver. We set the total profit area, or G11, as the objective. Tick the max option and then choose the range C11 to D11 in the changing variable box. Next, we add the constraints as required from the given information. Once that's done, choose Simple Linear Programming from the drop-down box and click Solve. Press OK, and we have the max profit of $55,400 by producing 1,000 collegiate and 975 mini.
Formulate the same model algebraically. To build an algebraic model for this problem, start by defining decision variables. In this case, the two decisions are how many collisions to produce and how many minutes to produce. These variables are defined. The C equal number of collisions to produce and the M number of minutes to produce. Next, determine the goal of the problem. In this case, the goal is to produce the number of each type of pipette to gain the highest possible total profit. Each collision yields a unique profit of $32, while each mini yield a unit of profit $24. The objective function is therefore maximize total profit equal $32 C plus $24 M. The first set of constraints in this problem involve the limited resource, the nylon and labor hours, given the number of pipette produced C and M, and the required nylon and labor hours for each. The total resource used can be calculated. This total resource used need to be less than or equal to the amount available. Since the labor available is in units of hours, the labor required for each pipette needs to be in units of hours, 3/4 hour and 2/3 hour rather than minutes, 45 minutes and 40 minutes. These constraints is as follows. And for the nylon, we have 3C plus 2M less or equal to 5,000 square feet. Labor hours, we have the 3/4C plus 2/3M less than or equal to 1,400 hours. The final constraint is that they should not produce more than the self forecast. The self forecast, the C, smaller or equal to 1,000 and the M, smaller or equal to 1,200. After adding the negativity constraints, the complete algebraic formulation is given below. We have the C, number of collisions to produce, and the M, number of minutes to produce, and the last one, we have the maximized total profit equal to 32 C dollar plus 24 M dollars. Subject to the nylon 3C plus 2M smaller or equal to the 5,000 square feet. Labor hours 3/4C plus 2/3M smaller or equal to 1,400 hours. The self forecast O smaller or equal to the C. The C smaller or equal to the 1,000 and the O smaller or equal to the M and the M smaller or equal to the 1,200.
Question C. Use the graphical method by hand to solve this model. First, we will start by plotting a graph with units of collisions on the horizontal axis and units of mini on the vertical axis like this. Then we need to plot the four constrained boundary lines, and the easiest way to do this is by determining where this line intercepts the two axes. So first, for the nylon constrained boundary line, 3C plus 2M equals to 5,000. Setting M equals to 0, use a C-intercept of 1,666.67, while setting C equals to 0, use an M-intercept of 2,500. Then the line is plotted like this. Second, for the labor constrained boundary line, 3/4C plus 2/3M equals to 1,400. Setting M equals to 0, use a C-intercept of 1,866.67, while setting C equals to 0, use an M-intercept of 2,100. And the line is plotted like this. It is the blue one in the picture. The next part is the sales forecast constraints. They are depicted as 1 horizontal line at M equals to 1,200 and one vertical line at C equals to 1,000. So a feasible solution must be below and to the left of all of these four constraint lines, and while being above the C-axis and to the right of the M-axis. Therefore, we have a feasible region, and it is shown as the highlighted area in the picture below. The optimal solution, an objective function line must be plotted by setting the objective function or the profit function 32C plus 24M equal to a certain value. For example, if I set 45,000 as the value of the objective function, the objective equation will be like this, and it is plotted as a black line in the picture. We know that all the other objective function lines will be parallel to this line, so we will slide this black line out as far as possible while still touching the feasible region to find the feasible solution that maximizes profit. This occurs when the line intersects the feasible region at the single point where C equals to 1000 and M equals to 975. And now the profit calculated is 55,400. Therefore, the optimal solution is to produce 1,000 units of collegiates and 975 units of mini, yielding a total profit of $55,400, the maximized one